Hey guys, so this is the third video in my series, and this is L'Hopital's rule for indeterminate powers. So like I said, this is the third video in this series. So in this video, just to be nice and clear, I'm going to be focusing on problems that kind of end up with these indeterminate forms. In video 1, I introduced all of these indeterminate forms and talked about L'Hopital's rule for just 0 over 0. And then in part 2, I talked about L'Hopital's rule with these forms. So like I said, we're just going to be focusing on this today. And L'Hopital's rule, so I'll just go ahead and show you kind of this again. So L'Hopital's rule kind of requires that we have this 0 over 0, or as we talked about in the last video, infinity over infinity form. When we get that, we can take the natural, we can take the derivative of the top and the bottom and then try to evaluate the limit. And so we talked about then in the last video, basically for, let's see if I come back to my forms. So for like these two forms here, we could only use L'Hopital's rule, like we could identify these, but then we had to kind of manipulate the problem to make this work. So if you watched video 2 and you understand that, then it's probably not too much of a stretch to believe that we also have to do some fancy manipulations for these types of problems. So I actually realized that my list is maybe not entirely complete. So for our video, or for our purposes, actually I'm going to add on one other power that I just kind of forgot about in the other two videos. So I've got 0 to the 0, 1 to the infinity, and also infinity to the 0. So all of these are fair game to use kind of this strategy. And so like I said, we're going to use a slightly different process for these forms. So the idea here is that if the natural log, if the limit as x approaches a of the natural log of f of x equals L, then the limit as x approaches a of f of x equals the limit as x approaches a of e to the natural log of f of x, which equals e to the L. And this can be for a finite or infinite limit, by the way. So what the heck does this mean? So don't worry, we're going to totally unpack all of this. So I would highly recommend that you have like this little statement here written down in front of you. And we're going to take a couple of examples to really unpack this, but this is really actually telling you exactly what you need to do. So you do want to have this kind of written down so that you can reference it and stare at it as we work through a few problems. And by the way, this is really relying on a fact that is usually presented like in algebra and pre-calculus. So this fact that e to the natural log of x will just equal x. This is a general fact, and so we're kind of taking a riff on that with this property that we are using here. Okay, so all right, so let's get down to this. I'm going to show you 5 examples here, but just FYI, I have more example videos if you want to see them, but I'm going to really try to draw out this particular technique. Okay, so here's the idea. So I've got the limit as x approaches 0 on the right of 1 plus x to the 1 over x. And so this actually will give me then that 1 to the infinity form that we're looking for. So we know that we've got to get clever. So where I want to start here is I want to play around with natural log and the manipulation. So first of all, let's call this in our heads, we want to call this our f of x. And again, remember, I want you to refer to that other property we're talking about as we go through this. So the first thing that I want to think about here is what is the natural log of f of x? So if I play around with this a little bit, okay, you should have a gut feeling of something that you should be able to do to this by taking the natural log of this. So I can use the power rule, bring down that 1 over x, so I know that this is going to equal 1 over x times the natural log of 1 plus x. Okay. So I see that. So let's see if I now use kind of this in my limit, what does that do for me? So let's play around with this for a second. And so I just want you to kind of go with me here for a moment. You might have some questions, and it's all going to kind of come back together in a moment. So what I'm going to do is I'm going to take the natural log of now this limit, and I'm going to do exactly the manipulation we just talked about. So now I can go ahead and do, let's see, the limit as x approaches 0. I can bring down that 1 over x. So now I've got this natural log of 1 plus x. So I want you to notice what this does for me. Let me get rid of this equal sign here. So this allows me to, oops, and this is still on the right. Okay, so this allows me to now restate this problem like this. And so notice now, what do we get with this? We get this 0 over 0 form because the natural log of 1 is 0 and then x equals 0 is just going to give me 0. So this gives me everything that I need to use L'Hopital's rule. So I'm going to just, ignore the fact that I took the natural log. We're going to bring this back together in a moment. So I'm going to go ahead and use L'Hopital's rule here. So I've got the limit as x approaches 0 on the right. This is going to be 1 over 1 plus x, all of that over 1. And now notice if I plug my 0 in, what do I get? I get 1 over 1, so I get 1. Cool. All right. But now we have to deal with that little problem of, but wait a sec, you totally changed the problem by taking the natural log. How can you do that? So now this is where we are going to resolve that by using this little guide here, okay? So this actually tells us exactly how to deal with this issue. The limit of my function is going to be equal to e to the natural log of f of x. And we figured out what this was, right? This is what we were just doing, right? We actually calculated this limit here. So these two limits are equivalent to one another, as I said, by using this little property here. You might have to take a second to stare at this to kind of get this to click. But then by doing this, then my limit will just be e to the L. So now we're going to leverage that property. So let me clear some space. And let's write this out exactly as it was. So remember, this guy here, this is my f of x. So what I'm going to do here is I'm going to write out that property. The limit as x approaches, so we'll say 0 from the right, of f of x equals the limit as x approaches 0 from the right of e to the natural log of f of x. And this was what we just determined. So this whole thing will just equal e to the 1, which was that limit that we calculated. And so that's how we resolve everything. And so there is kind of your process, I guess, for these types of problems. Okay, so let's do another one. All right, so now I've got the limit as x approaches infinity of x to the 1 over x. So just to verify that we got the indeterminate form, this is going to give us infinity to the 0. So we know that we need to do something here. So once again, remember, this is going to be my f of x. And so where I want to start with this is I want to think about taking the natural log of that function. So if I take the natural log of x to the 1 over x, I can rewrite this as 1 over x times the natural log of x. So now if I want to apply that to my limit here, if I take the natural log of x to the 1 over x, this is going to give me the limit as x approaches infinity of 1 over x times the natural log of x, right? Bringing down that power again. And then this is going to give me the limit as x approaches infinity of the natural log of x over x. So now I can rewrite this. And so now you'll notice I have turned this into a problem that gives me infinity over infinity. Therefore, I can go ahead and take the derivatives. So I take the derivative of the top. The derivative of the top is going to be 1 over x. I take the derivative of the bottom. That's going to be 1. And so now the limit of this as x goes to infinity is just going to be 0. So this whole thing will equal 0 over 1, which just equals 0. And so now we are good to go. So I'm going to go ahead now and use that property that we are kind of leveraging here. So the limit then as x approaches infinity of x to the 1 over x is going to be the same thing as taking then the limit as x approaches infinity of e to the natural log of x to the 1 over x. And this is the limit that we just figured out. So now I can just plug that limit in to get the limit as x approaches infinity of, oops, sorry, this is not, we've taken the limit, so I don't need that notation anymore. So this is just going to be e to the 0. And e to the 0, anything to the 0 power is just equal to 1. So that whole thing just equals 1. Okay, so moving on to C here, so same idea. So let's go ahead now and let's just jump right into it. So, so I can see just by looking at this, so what I'm going to end up with is infinity to the 0. So I've got that indeterminate form that I need. And if I go ahead and I just try to take the limit as x approaches 0 from the right of the natural log of 1 plus 1 over x to the x. So I'm just going to jump right into it now because I know exactly what I got to do. Now I can go ahead and say the limit as x approaches 0 on the right of x times the natural log of 1 plus 1 over x. And so now we have a problem. So you can see by looking at this that this did not work out like the last two problems, right? And that we didn't get something that was nice that I could just go ahead and have in fractional form and figure out. So now if I look at what I'm left with, well, this is going to be, this right here, this x is going to go to 0. And then this is going to end up going to infinity. So what I've ended up doing is now I just have a new indeterminate form. So now I've got to manipulate this, okay? So let's get clever and consider other manipulations that we can make. Well, if you watched video 2, you would know that one way that you can kind of manipulate this is that you can take this term here and rewrite x as equal to 1 over x. And that's equivalent to saying 1 over x to the negative 1, by the way. So this is a manipulation that is common with these types of problems. So let's see. Let's go ahead and see if that helps us. So now I'm going to have the natural log of 1 plus x over, oops, sorry, this is 1 over x, not 1 plus x. 1 plus 1 over x. Can't write today. I think I need another cup of coffee. Okay, so now I've rewritten this. So it's an equivalent form here. And actually, maybe just for our purposes, let's think of this for a moment as 1 over x. So think about what happens now as I take x going to 0 on the right. This we already said goes to infinity, and now this also goes to infinity. So now we have a third indeterminate form. This is now going to give us this infinity over infinity, but hey, that's great because now I can just take the derivative of the top and bottom. So let me go back to thinking of this as x to the negative first now that I've thought through that. Okay, so I'm going to take now the derivative of the top and the bottom. So let's see, actually I'm going to make some space for myself. Okay, so the limit as x approaches 0 on the right, this is now going to be 1 over 1 plus 1 over x. And then all of that times, let's see, negative 1 times x to the negative second. That would be the derivative of the inside. You have to use the chain rule on top. And then on the bottom, this will be negative x to the negative second. Okay. So now, let's see. We've got to play around with this a little bit. And you'll notice that I have x to the negative second on top and on bottom. So actually those and those negatives all cancel out. So this actually simplifies to something pretty nice. This is going to be the limit then as x approaches 0 on the right of 1 over 1 plus 1 over x. However, we're not quite done. So now if I think about evaluating this, so really the only x that you have here is that 1 over x. This whole thing is going still to infinity, right? So this is now 1 over x as x goes to 0 on the right, just goes to positive infinity. So that means then you've got really infinity in the entire, or dominating the entire denominator of this problem. And that's okay, because if infinity dominates the entire denominator, then really the idea of having 1 over something that's growing infinitely means that the entire fraction is just going to go to 0. So, a couple of facts, if that seems like kind of a lot, just a couple of things to think about. The limit as x approaches 0 on the right of 1 over x equals infinity. That's what is used right here. And then the other thing is the limit as x approaches infinity of 1 over x equals 0. So just two things you might want to refresh yourself on if this result seemed like a little bit much. Just these are kind of the two facts that I'm leaning on. So the fact that this went to infinity, if this is 1 plus infinity, that's kind of silly because infinity is just dominating the whole thing. So since we have infinity in the denominator, the whole thing's going to 0. Now, while it's great that we figured this out, remember what we were doing. I think this would be a really easy thing to forget, by the way. That's why I keep kind of going back to this. So we actually just found this limit here. And now we have to kind of round out this problem, right, by using, this kind of procedure or fact or whatever you want to think of it as. So I'm not quite done. So now I want to take a second. I'm going to think of this as my f of x, so I don't have to rewrite it. So now I just want to think about the limit as x approaches 0 on the right of f of x is equal to the limit as x approaches 0 on the right of e to the natural log of f of x. And so remember, this is what we were actually figuring out, was this limit here. So now I need to plug in that value. So this is going to equal e to the 0, so all of this just equals 1. And so now we're finally done with that one. Okay, so let's keep the party going. So now I've got, if I look at this, I can see that this is going to have that infinity to the 0 format. So I've got the limit as x approaches infinity of this x squared plus 2 over x plus 1, and then all of that to the 1 over x. So I'm just going to jump right into taking the natural log, and I'm actually also just going to jump right to bringing this exponent down. So I bring this down, I've got the natural log of x squared plus 2 over x plus 1. Okay, and so now if we just take a look at what we've got here, I can actually play around with this one and rewrite this as the natural log of x squared plus 2 over x plus 1, and then all of this over x. And so now you'll notice if I try to think through my indeterminate forms as x goes to infinity, this is going to give me infinity over infinity. So I can use L'Hopital's rule here. However, I might actually want to think through kind of this guy here for a moment, and if I want to simplify this, because as it stands, I will have to use the chain rule with this, but then I'm also going to have to use the quotient rule here, and I know that I can break this down a little bit farther. So I'm going to do that, so let me clear some space. And let's rewrite the top part of this. So I've got the limit as x approaches infinity of now the natural log of x squared plus 2 minus the natural log of x plus 1, all of that over x. And so while I still have to use the chain rule here, at least I don't have to use the quotient rule. So now I feel comfortable taking the derivative. So let me clear some space again. And now let's go ahead and take some derivatives. So this is going to be 1 over x squared plus 2 times 2x minus 1 over x plus 1. That's the derivative of the top, and then in the derivative of the bottom I just have 1 here. And so now let's see, let's keep having to clear space for myself, but let me do that again. Okay, so now I can see what I'm really left with here is 2x over x squared plus 2 minus 1 over x plus 1. And so now that's what I have to take the derivative of. And so I can tell by looking at this, this is going to go to just 0. So now I just have to think through this particular one. And so notice that the dominating term is in the denominator here. So this whole thing is also just going to go to 0. So this whole thing is just going to equal 0. All right. Now, here's the fun part. So don't forget what we were actually trying to do. We were in the middle of trying to use this whole little procedure, right, this trick. And all I've done so far is I've just taken this limit. So I still have to finish this. So I think that would be a really easy thing to kind of forget because you go through all this work to find the limit. So now I'm just going to go ahead and finish this. So let's see, I'll clear some space one more time. Okay, so now I can go ahead and leverage this, that I'm taking the limit as x approaches infinity of, let's see, I'll just write this out as f of x so I don't have to write this whole thing out again. So this is f of x. So, all right. The limit of f of x is going to be equal to the limit as x approaches infinity of e to the natural log of f of x, and this is the limit that we just determined. So this is going to equal e to the 0, so all of this was just to get the limit of 1, and so we're good. Okay, and so I have just one more here just to kind of round out this, so hopefully you feel like I've done a decent breadth of problems. So just notice here, this one is going to give me 0 to the infinity. So I'm going to have that indeterminate form. So I know what I got to do. So I'm just going to go ahead and leverage kind of some of the work work right away. So this is, I'm going to bring down that power and I'm going to write the natural log of the natural log of x. Okay, so let's see what we get with this. So if I just now try to play around with this fraction, the natural log of the natural log of x over x minus e. So in this case, now this is actually pretty straightforward. This is going to give me, well, let's work this out. So this is going to give me the natural log of the natural log of e. The natural log of e is going to equal to 1, and then the natural log of 1 is equal to 0. So this is actually going to give me 0 over 0 in disguise. So this actually just now our classic L'Hopital's rule, so we're good to go. So we can take this derivative here. So let me clear this out. And now let's take the derivative of the top and the bottom. So I've got to use mega chain rule here. So it's going to be 1 over the natural log of x. Let's see, 1 over the natural log of x times 1 over x. And then in the denominator, this will just be 1. So now I've got the limit as x approaches e on the right of 1 over x times natural log of x. And so now I can actually just plug e right into this to get 1 over e times 1. So it's just 1 over e. Okay, now remember we're not done. We still have to plug all of this information in. So let me clear some space. Okay, so now I want to take the limit as x approaches e on the right. I'm just going to refer to this as my f of x. So I want to take the limit of this, which means then that's the same as taking the limit as e to the natural log of f of x. And we just figured all of that out. So this is going to be the limit. Let's see, the limit. Actually, I don't have to keep writing the limit down, and I don't mean to. This will be e to the 1 over e. And so that would be our limit in this particular instance. So you now kind of see all the different ways that these types of problems can go. So hopefully that was very helpful. I'm not going to have covered everything. You still have to kind of think, and there could be other things that come up, but hopefully this kind of gets your creative juices flowing, and now you can kind of come up with some ideas on your own in your own homework. Thanks for watching, guys. I'll catch you next time.